Hello everyone. Thanks for joining today's session. And TensorFlow User Group Kolkata has been in the slumber for a while, I would say, because of the Amphan and all of that stuff. But hopefully, here we are back again. So today we have a very special guest with us, Kolkata's own boy, Dipanjan Sarkar. He of course doesn't need any introduction because I myself am a fanboy. I have read many of his books and blog posts and stuff. Although he doesn't need any introduction, I'll repeat myself. I'll just formally introduce him and then he can take it away. So Dipanjan Sarkar is currently a data science lead at Applied Materials. Before joining Applied Materials, he worked at Red Hat, Intel, and so on. He is also a Google Developers expert for machine learning. He has authored multiple books. I'm sure you all know about that. So without anything from my end, I'll just hand it over to Dipanjan. So Dipanjan, take it away.
Sure. Thank you. I'll just share my screen. Give me a second. I hope it's visible. Can you just confirm once?
Yes, your screen is visible. You are audible as well.
Excellent. Okay, thanks a lot everyone for joining in on a Sunday. We'll be covering some basic concepts with regard to natural language processing from a practical perspective as to what are the key things you would need to know if you are to start applying NLP in your own problems, or let's say if you want to learn NLP, what are some of the key things which you should know and in what order. Then we will look at some popular applications of natural language processing, maybe dive into some of the tutorials using some hands-on examples, and at the end we will also look at a couple of case studies which I solved a while back leveraging natural language processing. So overall, this is the high-level agenda: a brief introduction, and then talking about what is natural language, understanding what is natural language processing and why do we need it, the motivation behind natural language processing. And then we'll cover some of the most popular applications out there with regard to leveraging text data or natural language. And we'll cover a standard NLP workflow. And then we'll move on into the hands-on tutorials with regard to leveraging some open source frameworks. Some of you might be already aware of these. And we'll tackle two problems. And finally, we'll go into the industry case studies. So a brief introduction about me. I think Saik has already introduced me, so thanks a lot. I'm currently working as a data science lead in Applied Materials, and besides that, I also work as an advisor / consultant with various companies and startups, including an edtech startup Springboard, and also a Google developer expert in machine learning. And I've written and published several books, articles, papers in this area of data science. So feel free to check it out. I'll share some social links towards the end of our talk. So this is the slide deck and the hands-on examples. So basically the code is available in this URL. You can just take a note of this. Someone can maybe type it into the chat also. So in case you want later, the content is available to you. You don't need to like take snapshots or memorize things here because everything will be available later. So just focus on basically what I'm trying to say, and that will be useful. I'll just pause here for a couple of seconds and then I'll move on to the content. Okay, so moving on. Let's start with understanding what is natural language before we go into natural language processing, because this whole field called linguistics has been there for a long time. It's nothing new. And NLP, as we'll talk about, is applied linguistics. So natural language is basically a mechanism using which humans communicate with each other, and now basically with machines because of this whole advent of NLP as a field. So the idea here is natural language is very different from a constructed or a programming language. And the reason here is because it is very unstructured in nature, as well as there is this whole aspect of context, semantics, meaning that is, and ambiguity, sarcasm. The same word might mean different things in different contexts. So you get the point. In case of a programming language, which is also known as a constructed language, there is a fixed set of constructs, as you know, like the keywords. There is a fixed set of flows like conditionals, if else, or let's say loops like a for loop. And I guess most of you must have done electronics as a part of your coursework. In case you took engineering, in case you didn't, it's basically where you learn something called the assembly language, if you think about it, where there were very fixed constructs and you would need to go through them, and it would execute sequentially. They were known as opcodes, if you remember. So that's where everything is very constructed. And human language is very unstructured in nature. Like I'm talking to all of you right now. This is basically natural language, because there are so many languages in the world. And even if you consider only English, so many types of meanings in different contexts, so on and so forth. So that is why it's very difficult to parse and comprehend this language directly by machines. Because when I'm talking to you, thankfully, due to all the knowledge and the world view which is there in your brain, you're able to comprehend what I'm saying. But for the machine to understand it, it is a challenge. And that is where NLP as a field comes into perspective. And text data, just to kind of motivate the problem, it's available in a wide variety of forms like emails, messages, blog posts, log messages, documents, so on and so forth. So let's dive into what is this whole field called natural language processing. To motivate this, there is basically three main fields. Like I was talking about earlier, you have linguistics on one hand, you have artificial intelligence on the other hand, and you have computer science in the third area, if you think about it. So NLP is basically an intersection between all these fields. The reason being that to understand a language with regard to its morphology, its meaning, semantics, so on and so forth, you need the linguistics aspect of things. To be able to program or code, you will need the computer science aspect of things, where you will need to implement some programs or some systems and so on. And for implementing data-driven intelligence, that is where you need this field called artificial intelligence, because you would need to code in a way that you consume the data and you are able to build an intelligence on top of it using, let's say, machine learning or deep learning. It's not like you can code a fixed set of rules that, okay, if word A is encountered, translate it to word B, so on and so forth, because you need to build these scalable systems. So NLP, in short, is a field which is an intersection across these three fields. And it's mainly concerned between understanding this interaction between the computers and the natural languages. And the key focus, as you can see here, is to train these machines or computers to be able to process this text data, analyze it, understand or comprehend it, and be able to model some kind of a complex cognitive application on top of it, which can be difficult to solve with just traditional machine learning or deep learning. You would need to do some level of processing before that, and that is the whole premise of natural language processing, so that computers can perform these really complex cognitive tasks which wouldn't be possible otherwise. And just to demystify some of these terms, in some blogs or in some books, you may see NLP being mentioned, like natural language processing. Some might mention text analytics, and some might mention text mining. So overall, these three things kind of mean the same thing. The idea is to understand applied linguistics. How do you extract the information from natural language and you apply all these techniques to that? So that is where I think you need to understand that whenever you have any kind of a corpus of documents, or corpus known as a collection of documents, the methodology you follow to extract insights out of this by leveraging, be it open source or commercial tools, that is this whole thing called either NLP or text analytics, or mining for insights from this text data. Text mining. So now moving into why natural language processing. So natural language processing, the motivation behind this can be explained in a few ways. One of these is an interesting quote from Yahoo Research, where he mentions that the bulk of information value which is perceived is coming from data in relational tables. So if you think about most enterprises, if you're already working in one, or let's say you are interested to work in one, you will see that most of the time when people get started with, they will start with what is called as descriptive analytics, where they will tap into a relational database, like a SQL database consisting of so many tables. So in short, structured data. And they will start extracting insights out of it. So the reason behind that, it's easy to extract this information. You just write a bunch of SQL queries, or you, let's say, take pandas in Python, do a group by, and you start getting some insights with regard to describing your data. So this has given the general notion that a lot of the data from which we can get insights is in this relational format, but that is not always the case. And the reason behind that is, if like a lot of enterprises have done this assessment, and they have seen that 80% of relevant information in an enterprise is in unstructured form. What I mean by that is basically in the form of text or images or speech. And that is where the true potential of tapping into more insights lies, not just only relational data, because you get limited in terms of, let's say, your features or the insights. A lot of things will be in this unstructured text data. And that is where the NLP, the motivation for NLP comes in, as to 80% of the world's data is in unstructured, or let's say semi-structured text data. And the idea is, based on the domain you're in, be it you're analyzing social media data, or you're analyzing enterprise documents, records, log messages, so on and so forth. How do you extract the right kind of insights from this? And in short, again, this is not to demotivate people who are working in the area of image processing or computer vision, but realistically, if you consider all types of industries out there in the world, or all types of domains, it is not like every industry will be using text data. So if you think about it, like detecting traffic or finding out the vehicle density in a road, it is not like you will be doing that everywhere. There will be, or let's take healthcare, for example, like trying to diagnose scans with regard to the human body. So you will not be doing this kind of work in each and every domain, but more than often consider healthcare, oil and gas, regular enterprises, IT shops, whatever be it, you will have typically some form of useful text data which needs to be processed and analyzed. So again, just to motivate the fact, often you may, this is more like if you're starting off in this field of data science, you may get really hyped up thinking that I can maybe do some image captioning, or all these cool aspects you're seeing with GANs, where deep fakes is coming up, where you're generating fake images, or even doing it on video. So those could be cool applications. But if you think about working day in and day out in an enterprise, those are not the things you would be doing all the time, right? You wouldn't be sitting and building an image captioning model, or you wouldn't be sitting and building like fake images. So just to think on those lines, if you really want to understand that why do I really need to learn NLP, this is the exact reason that almost some form of text data is present in most companies. So it is good to know at least how to understand and process this data. And again, coming back to computer vision as a field, it is pretty good. It is not to undermine that. Like even I'm myself solving a lot of varied problems in computer vision. But if you think about the scope, remember, if you're only interested in those kind of industries which relate to working on image data, then you should definitely even learn that too. So just something to keep in mind. And now this is the most important aspect, the practical aspect of things. So most NLP models now are realistic and affordable. What I mean by that is, most of these models out there which are building, thanks to open source frameworks like scikit-learn, Spacey, NLTK, and even transformers, let's say coming in from Hugging Face, TensorFlow, Keras, PyTorch. So now you can leverage all these powerful tools and build your own models. So that is why it has become affordable to build these models, and it is realistic because thanks to aspects like transfer learning, where these models have already been pre-trained for you by running on GPU clusters for days, let's say. You can leverage these huge models and use it out of the box to do useful things like question answering, translation, so on and so forth. So that's why it has become kind of realistic for even a standard person to solve these problems. And not really worry about that you have to be in a company environment. Like you can use resources like Google Cloud, Google Colab, and you can even build these models. So it has become realistic nowadays to build these models. Consider 30 years back, was it possible? You still had NLP as a field, but it was very theoretical. You didn't have enough data, you didn't have enough compute, you didn't have all these pre-trained models available for you. So nowadays, thanks to all of this, you have basically realistic models which can be built for NLP, and you can even deploy these models now thanks to a lot of frameworks out there, be it TensorFlow serving, Flask, Django, whatever be it. You can potentially deploy these and build an entire end-to-end system. So just something to remember with regard to the motivation behind NLP. Moving into NLP applications, so what are some of the popular applications of NLP? So I'll use a popular image which is pretty much used everywhere. So these are some of the most popular applications of NLP. One is information retrieval. So basically that is used in search engines where you type in some text, and based on some mathematical constructs, like it tries to extract relevant features from your input text data, and it tries to match against features of all, let's say, web pages which are out there, the content of the web pages. That is what Google is doing. And then it does some kind of a ranking using some mathematical metrics like cosine similarity or Jacob similarity, and it tries to find out that looks like these are the top 10 documents or web pages which are most relevant to your query. So this whole aspect of retrieval, the whole aspect of feature vectorization, retrieval, ranking, relevancy ranking, and returning the results, all of this falls under this field of information retrieval. Sentiment analysis, I guess none of you are new to it, so I won't dive into too much detail, but the idea is to get feedback from natural language text data with regard to your products, services, and so on, based on the sentiment the person is exhibiting when they are typing in that review or typing in that survey feedback. Information extraction is all about extracting the right kind of insights, relationships, entities from unstructured text data. So this could include extracting the key named entities, like whether this is a person, whether this is an organization, a date, a payment amount, and then potentially trying to find out relationships based on like a subject, verb, object construct that, okay, think about it like dependency parsing as it is known as. So object A is causing object B to do something, or object A is related to B in this relationship. So basically that is where information extraction comes in as a pretty nice application. And then obviously machine translation, none of you are new to it. Basically when we are translating from one language to another language, or translating from speech to text or text to speech, that is where NLP is being used in the back end. For the folks who are more interested on the technical aspect of things, what is being used in the backend is like an encoder-decoder model where the data goes into the encoder and the translated sequence comes out of the decoder. Earlier sequence-to-sequence models used to be used where the data used to go in as a sequence. Nowadays with transformers, the whole sequence goes in parallel. So the encoder-decoder architecture still remains. The way in which it is used changes based on the type of deep learning model which is being used. For the people who kind of already know this, those who don't know this, don't worry about it. Once you learn about machine learning and then dive into deep learning, you will come across these terms. Question answering, I think pretty much everyone can understand what that is, where you have a context or a database, and the idea is if someone asks a natural language question, can the machine reply back in the form of a human-generated response? So that is where it's being used in chatbots and question answering tools with regard to, again, kind of like a search engine where people can type in a question and the answer comes out, things like that. So these are some of the popular applications for NLP. And if you think about it, there are many more applications and many more, you can say, constructs of natural language processing. So this is where you can see some overlap that, okay, if I'm trying to cluster or group documents together, and if I'm trying to classify documents into which class or category they may go into, as you already know, classification is a supervised machine learning problem and clustering is unsupervised. There are still some aspects which are common amongst them, like feature engineering or feature generation. So that is something we'll talk about later. So just something to remember from here is that a lot of the concepts related to these applications are overlapping or common, and that is exactly what we'll talk about when you go into the NLP workflow, as to what are the key steps in sequence, and some of these steps typically are common regardless of the application you're trying to build. So I've summarized the most common NLP use cases in this slide. So folks who are interested, feel free to check it out. And it even has some level of high-level examples. So text classification, probably 80% of the time, the most common use case in the industry, where you're trying to categorize documents based on some known labels. So that is where we have historical label data, and you build a classification model on top of this so that you can categorize a new text document. Can be used in examples like I have a support ticket coming into an enterprise. How do I route it? Should it be a critical category, a high, medium category, or what is the root cause of this ticket? So you can do that kind of a classification. And then you have aspects like news article categorization. So if a news article comes in, whether it will belong to sports or whatever, politics, business, current news, things like that, you can categorize it, given that you have trained a historical label data, a model on top of that. Text clustering, again, as the name sounds, it is grouping similar articles together, and you can use it for detecting almost duplicate documents with fuzzy matching and text similarity. You can build content-based recommender systems where you look at the text data and try to say what is similar to new input text sequence of words. So that is an example we will look at towards the end of the presentation, where we cover a simple movie recommender system. Search and information retrieval, I'm pretty sure we just discussed this, where you are ranking documents based on relevancy, and it's being used in search engines. And just something to remember here is that the search engines are not just something which Google or Microsoft is building. If you're working in a company, often the unstructured content in a company needs to be searchable. So that is where you can leverage these concepts of natural language processing, coupled with already matured search engine frameworks like Solr or Elasticsearch, and you can build really effective search engines. Next one is like parsing and named entity recognition to extract key entities from any kind of documents, like legal documents, understanding contract key entities, or extracting documents from health records. Parsing also is a very important construct in terms of optical character recognition. If you think about it, the OCR applications where you are digitizing a document, you are scanning it, getting a PDF, and then you're trying to extract, or images, and you're trying to extract the text content from that, parse it to find out relevant entities. So that is where parsing becomes very important. Text summarization, as the name suggests, you have to potentially take in any kind of big documents and summarize them. Maybe you can find out some of the key trends by using topic modeling. And then you have machine translation, where you are translating from speech to text, text to speech, from one language to another language. Conversational interfaces we just talked about, be it chatbots, assistants, or the question answering systems. That is where it's being used. And sentiment analysis, nothing new about it. When you have survey results coming in, or you have what is called as a net promoter index results coming in, you can analyze the unstructured responses and potentially find out whether the overall sentiment is positive or negative. You can even do something called as the aspect-based sentiment analysis, where you try to reason as to what is the cause of a negative or a positive sentiment. Okay, I have enough time. Going into the standard NLP workflow. So this is something I had built, I think, years back, but again, you can modify it in any way you will, but the core concepts remain the same. So initially you start off with some level of text documents. You pre-process this text document. So what I mean by that is usually your text data may be noisy in terms of having HTML characters, special symbols, aspects like that. And based on the type of application or problem you're trying to solve, you may need to do some pre-processing. So that is where this text pre-processing block comes into focus. And once you're, and by the way, just to recap, a collection of text documents is known as a corpus. So once you have pre-processed your corpus, what you do next is, based on the application, again, if you want to gain some initial insights, you may need to parse this text data, you may need to do some exploratory data analysis, understand your key phrases which are occurring, keywords which are occurring, do some relationship analysis. So that is where this this block is again optional, but depends on the type of problem you're trying to solve. The next part is basically the text representation and feature engineering, or I would say feature engineering, because it's all about being able to represent text data in a way which is understandable to the machine. So as you know, when I'm speaking to you, you can automatically understand it thanks to our super cognitive capabilities in our brain. But what about machines? So for those of you who already know machine learning and maybe deep learning, you might know that at heart, all of these are math-based models, right? There is some level of optimization happening. There is some level of relationships being extracted, and the way it's represented is in the form of mathematical operations, usually dot products or matrix multiplication. So typically features are represented in numeric matrices, and some operations are happening on them, be it some derivatives or some gradient descent, aspects like that. So what I mean by that is you can't just feed in text data directly to a machine learning model or a deep learning model, because if you try to feed in the text data, it will immediately error out, because these models can only understand numbers. So how do you represent this text data, these words or these sequences of words, into a numeric representation? That is this whole concept of text representation. And nowadays, since deep learning is being used to do some of this, it is also known as a subfield called representation learning. So I would recommend people who are really interested in this area to check it out, where representation learning is all about using neural networks to encode this information of text into a numeric vector representation. So that is called also as feature engineering, because we're trying to extract numeric features from this text data. And once your numeric features are already extracted, you can potentially apply it to any downstream task. So from here on, starts your downstream machine learning or deep learning task, where you're either doing classification, you are doing regression, you are doing summarization, similarity analysis. So that is where you can apply the relevant deep learning or machine learning models here. And once you have the right type of model, it's evaluated based on some performance criteria, as you know about it, like accuracy, ROC, precision, recall, false positives, all those aspects. And once the business gives you the buy-in, or let's say if you are building a project, you yourself decide that, okay, this is the best model in terms of complexity, performance, and so on, that is where you go ahead and deploy the model. So overall, this is the standard workflow of any typical natural language processing project. And for the people who are already doing deep learning for natural language processing, just to recap or revisit some of these workflows, though I won't be covering since this is an introductory talk, but for people who are interested, when you go into deep learning, it is recommended you keep the pre-processing to a minimum, and you basically, what happens is typically the model themselves can handle most of this. Of course, you may need to represent your text in the form of embeddings and so on, but for even the more complex models like the transformers which have come up recently, the transformer block can pretty much take in this whole context. You would just need to format your text data in the right way. So just as a tip for people who might want to dive deeper into this later. So coming to text wrangling, what are the key steps here? So some of the key steps involve removing HTML characters, extra white spaces and new lines, some symbols. In case we want to remove numbers, we can even do that. Converting accented characters to a standard ASCII format, stemming all lemmatization. Again, the emphasis is on or. Typically, you don't do both. You should do either one of them. Stemming is based on fixed rules. may give you a dictionary incorrect word, but lemmatization will give you a lexicographically or a dictionary correct word when it basically gets a word into its base form. So it removes the inflection, the suffix typically, or an affix, and it gets the word back to its base form. You can remove stop words also, which are words which don't carry much information. And these are optional, again, if you really need to tokenize or do some spelling or grammar checks. Maybe I'll just briefly show this in an example. So just again to recap, if you want to go to the hands-on examples, you just go to this URL, NLP1 bit.ly NLP101 underscore DS, and that will redirect you to the GitHub repository. So there are a few notebooks here. I will try to cover at least most of them today, and then we'll look into how these things are working. So again, some basic dependencies like using the NLTK package and so on. I won't go into details due to the interest of time, but given that I have well some time left, some of the key steps here could include case conversion, where we are translating the text into or converting the text into either lowercase, uppercase, or title case, where every word is in uppercase, the first letter. So usually lowercase is what is being used when you're working with text data and doing some kind of case conversion so that all the words are in the same case. Tokenization, again, assuming you have a big document here, as you can see, multiple sentences, what you can do is you can extract out the sentences. So how many sentences are there? So you can extract out each sentence. That is where you can use the NLTK sent tokenize function, or if you want to extract out all the words in this document, you can use the word tokenize, which extracts out each and every word. And nowadays, Spacey has come out, which is a really nice library with a lot of features. So you can even use Spacey. All you need to do is load up Spacey given a language model. Typically, you start off with an English language model, but they have different language models. And what you can do here is wrap it up in this NLP construct, and then you can use a list comprehension where you say, extract out each of the sentences using the .sense attribute, and you will get the same output as you can see from before, all the sentences. And if you remove the .sense attribute and you use the .text attribute here for each and every token, you will get back these tokens, which is basically the word tokenization. So removing HTML characters was our first point of interest. So let's say you're doing some web scraping. This is the kind of content you're getting, as you can see. So it's filled with a bunch of paragraph tags, and then you have, as you can see, paragraph tags and line breaks and so on. The idea is to extract the text content out of this. So that is where these are the things which you don't need. So that is exactly where we use a library called Beautiful Soup, and you tell it that the content I'm feeding you is HTML content. So use your HTML parser and extract out any kind of script tags or iframe tags, remove extra new lines, and give me only the text content. And as you can see from this block of text with all these tags, we are getting some clean text, which is the content of the book, which we are trying to extract. So you can reuse this function also if you want, enhance on top of it, and so on. Accented characters, like I said, sometimes there could be non-English accented characters. So if you're dealing with an English model, you can just translate it to an ASCII format and get back an English token. How that helps is because if you had the token text also, it may be perceived differently if you had this. So to make the model understand that it's the same, that's where you need this. Of course, if you're dealing with a different language with accents, then you shouldn't be doing this because an accented E might mean a different thing in their language. Removing special characters, numbers, and symbols. Again, this is where we can use a simple construct like a regular expression where I tell it that if I want to keep the digits in the text document, then keep everything which, and by everything I mean each and every character which lies either between small a to small z, capital A to capital Z, or between 0 to 9, and retain the spaces. So this pattern does exactly that. And if I want to remove the digits, then I just check for this pattern, which means anything which is an alphabet or a space, keep that in and remove everything else, which includes non-alphabets and digits. So as you can see here, if I call this function and say remove digits, true, only the alphabets and spaces are retained. And if I say remove digits is false, only the symbols are removed and the numbers are retained. Depending on the use case you're trying to solve, you may need to even keep the specific special characters, like if you're trying to extract a payment amount from a expense report, you may need to keep the dot if you think about it. So those are the things you need to keep in mind, that this is not the only way to do things. This is one of the ways. Contractions are basically words where we remove some of these parts of the word and or multiple words, and you put an apostrophe to kind of give a contracted or a shortened format. So as you can see here, like I would be I would, and wouldn't would be would not, and so on. So there is a library called contractions. You can use that and fix every word related to your document. In this case, you can pass the sentence directly, and you can see that it has expanded all the contractions from before. So it's basically doing a simple pattern matching and expansion, like wouldn't becomes would not, and so on. So that is something which can be useful for you to, again, normalize or standardize your text. Stemming, like I said, is to come back to the base form of the word. In this case, it is known as a root stem. It uses a bunch of rules where it can say that if the word is ending in ing or s or ed, chop off this and come to the base form. There are different types of stemmers, like Porter stemmer, a snowball stemmer, Lancaster stemmer, and so on. You can even check out the source code in NLTK, and you will see there is a bunch of rules which it uses to come back to the base form of the word. Some of the issues with stemming could be that the base form, like strange or stranger, can come back to strang. So that is where you may get a base form which is not a dictionary correct word. So if you're only concerned about syntax, you can use this directly. But if you're concerned about semantics or the interpretability of your models, you can go for lemmatization. So lemmatization uses a dictionary, like I said, to say whether the word is going to be a dictionary correct word or not after we remove the inflected form of the word to come to the base form. In this case, it is known as a lemma, not a root stem. So the lemma is a dictionary correct word, which typically is formed by checking the dictionary when you are trying to lemmatize a specific word. And for that, you need to know the grammar, which means you need to know the parts of speech of each and every word, like whether it's a noun or whether it's a verb, so on and so forth. So as you can see in this case, we know that cars or boxes are nouns, so we pass an N and we get car and box. Running or ate becomes run or eat, and as you know, these are verbs. Saddest, fancier, as you can see, these are adjectives and become sad and fancy. And as you can see here, if I by default, the tag is taken as a noun. So if I don't pass the tag, or if I pass in a wrong tag, the lemmatization doesn't work. It's known as an ineffective lemmatization. So that this is where parts of speech tagging become important. So as you can see here, if we have this sentence, the brown fox is up and they are jumping over the sleeping lazy dogs, you can tokenize this. And if you lemmatize this directly, you can see a lot of the words are still not lemmatized, because when you're lemmatizing every token, it only lemmatizes the nouns. Everything else it considers as a noun, so they are not lemmatized correctly. So how you correct this is, first you take in the parts of speech tag by using the pause tag function from NLTK. You map it to a WordNet format of the tags, because NLTK lemmatizer is based on the WordNet dictionary. So you need to map these, like JJ is an adjective and so on. And NNS is like a plural version of a noun. CC is a coordinating conjunction, and so on. So whatever is there, you just try to map it to only nouns, adjectives, verbs, and so on. And this is, as you can see, the new parts of speech tags, which we do by using this mapping function. And once this is done, we can call the lemmatization for every token based on the specific parts of speech tag. And now you can see that we get some effective lemmatization here, where jumping, sleeping, all of this has been corrected to the right base form or the lemma. And you can reuse this function if you want to do your own lemmatization. Spacey has a even easier version for you, where you can just call the lemma underscore if there is a lemma present, and if it's not a pronoun, then you convert it, else you keep it, because Spacey converts the pronouns to this symbol called the PRON, which is the short form of pronoun. So I just keep them as they are, and whatever is not a pronoun, I convert them to their lemma, and you get the same result. So you can consider using Spacey. But just to show you the inner working of it, how NLTK does it, I just went through this. So hopefully that gives you some perspective. Stop word removal is basically removing stop words like I discussed. So you can remove words which are not useful, like articles, conjunctions, prepositions, and so on. And these are the words which usually carry little meaning. So you can remove these words. If you have your own stop words based on the problem you're trying to solve, you can add in your own stop words also and remove them. So by default, NLTK gives you a standard list of English stop words, as you can see here. You can remove your own stop words from, you can add in your own stop words, remove some stop words from here as necessary. So coming to text representation, this is where we take in the text documents and try to convert it to some level of a numeric representation, as I was talking about, because machine learning, deep learning models can't really understand unstructured text directly. Some of the common models are bag of words, topic models, TF-IDF, similarity-based metrics, word embeddings. I think word-to-vec glove, fast text, these are some of the most common embeddings out there. And there are more complex ones nowadays with contextual embeddings like Elmore, BERT, and so on. So let's talk about traditional text representation models, which have been there for quite some time. The simplest model is known as the bag of words model, where every document can be represented by a vector of words. So you represent a complete document into a vector where every element in the vector is a specific word which is occurring across your corpus. And the value in the vector is the number of times that word is occurring. So overall, the vector depicts the number of times each and every word is occurring in that document. This will become more clear once we look at an example. A bag of n-grams is same as a bag of words. So instead of the words, we have n-grams. And basically, we try to count the number of times those sequences of words are occurring, like 2 words in sequence known as a bigram, 3 words in sequence known as a trigram, and so on. TF-IDF is basically a normalized version of this bag of words model, where we count the number of times every word is occurring in that document, but we also divide it by the number of times that word is occurring across all the documents, which is known as the inverse document frequency. So in the document frequency is the number of times a word is occurring across all the documents, and inverse document frequency is the inverse of that. So you can imagine if a word is occurring in 99% of the documents, its document frequency will be huge. So if you take an inverse of that, you end up with a very small floating point number. Now you multiply that with the frequency of that word in that document, the final value will be very low. So essentially those words are like stop words because they are occurring in every document. So they don't really contribute much to the variation across documents. So that is where we can downplay the effect of frequently occurring words by multiplying this frequency with the inverse document frequency and get a normalized frequency. Document similarity is where we are trying to derive features from a base feature vector like bag of words, or could be even embeddings, where we use something like a cosine distance or a cosine similarity to find out how similar every document is to the other documents using a score. So higher the similarity, let's say closer the score will be to 1. So often this is known as the pairwise similarity, where we are trying to see how similar every document is to the other documents. And this is very useful. And we will actually use this in a hands-on example later on, where we do the movie recommendation system. Word embedding models, again, I won't go into too much detail considering the time we have at hand and also the nature of this session being an introductory session. But for people interested, this is where we use some level of neural networks or some level of contextual understanding to see that how similar every word is to the other words. So we try to look at every word and the surrounding words and try to generate a vector representation of every word. Remember earlier, every document was converted to a vector. Every word was a count. Now every word has its own fixed sized vector known as a dense vector. So the whole concept behind this is that the word is known by the company it keeps. So similar words will have similar vectors, and words which are not being mentioned in the same context will have different vectors. So that is where people who have read the Word to Vec paper may know this man, king, and the queen, woman. So that is where you look at the semantic similarity by seeing words which are mentioned in closer context will be closer to each other. And there are different ways of doing this, like Word to Vec looks at every word and tries to find out similar words close to that word using continuous bag of words of the skip-gram model. FastText does a similar thing to an extent, but it considers a word as an average embedding representation of subwords. Like the word where will have an embedding, which is an average of these subwords of that word. So FastText uses a bag of character n-grams versus using a word-based embedding system, and Glove uses a matrix factorization context to give dense word embeddings. Let's just quickly look at some examples here. So you can check out this notebook in more detail. It'll explain you everything. Due to the interest of time, what I'll do is focus on the outputs. So these are various documents. As you can see, we have typically one sentence each. Some of them are talking about the weather, some of them about food, animals, and so on. Now, what we do first is we take in these documents and do some basic text pre-processing, which means removing special characters, lowercasing, spaces, removing stop words. So you can see that the sky is blue and beautiful. This becomes sky blue beautiful. So you get the point. We are lowercasing, removing the stop words, and so on. And now we want to convert these into the numeric representation. So the first one we talked about is a bag of words, which converts it to this representation. So every document, which means this first document, the sky is blue and beautiful. After pre-processing, it becomes sky blue and beautiful. And after the feature vectorization, it becomes this vector. So what does this vector mean? Basically, it is the count of the number of times specific words are occurring in that document. So in a more human interpretable format, this is the output vector of our first sentence or first document. And as you can see, beautiful, blue, and sky are occurring once. So these are one. In case of the sixth document, it is basically the sky is blue and the sky is beautiful today. So this is the pre-processed text, and you can see sky is occurring 2 times. So correspondingly, the value for sky is 2. So this is the vector representation of each and every document which we get and which can be fed into a downstream machine learning or deep learning model. For bag of n-grams, instead of words, we also look at n-grams. So in the second document, we talked about the beautiful blue sky, most probably, as you can see. So that is why, since we talked about the I love the blue beautiful sky, that is why you can see here that beautiful sky, since they occur in sequence, that bigram is occurring once. So that is why we have 1 here. So this is where you can use bigrams, unigrams, trigrams, and so on. The TF-IDF model is the normalized version. So if you use the TF-IDF vectorizer, you can see you get some floating point values because they are the scale version of these term frequencies, which we talked before. For document similarity, it is a pairwise similarity. So if you remember, we had around 8 documents from 0 to 7. So what we are trying to say is, if I input you this matrix, so as you can see, let's talk about this briefly. Let me see, okay, given the time we have. So you can see that this vector, these two vectors, if you think about it, yeah, very similar to an extent. The same non-zero ones are close to each other, and in this case there is one difference, but otherwise it's very similar versus, let's say, this vector. So once we compute the similarity, you see that the first document is very similar to the zero document, almost 82%, and these are not at all similar. So that is where we can find out how similar one document is to the other documents, and we can even use this in the future. So again, clustering is where I'm doing unsupervised learning. So if I know how similar every document is to each other, I can find out the groups by feeding this into an algorithm like k-means. And you can see that even if I didn't have the category, the model has correctly identified that these belong to one category, the animals belong to one category, and so on. So that is where similarity-based features or even TF-IDF-based features can be useful. For embedding, due to the interest of time, I won't go into too much detail, but for people who are interested, you can check this out, where we can use, again, the same documents I've been using here, but you can use something like Word2Vec from Handson, and you can set the feature vector size. So typically it is taken as 300 in case of most pre-trained models. So this is basically the dimensionality of each of the word vectors. And you can put some context as to how much back or how much forward it should look around it. And then you can say whether it's a skipgram or a continuous bag of words model. That is the type of neural network architecture being used to train this. And you can see this kind of output where every word has a vector representation. So if you take a dimension reduction plot, you can see that similar words mentioned in the context will be grouped close to each other. So obviously, sky is more close to blue because they have been mentioned in the same context. And if you want to see the numeric representation of sky, it is basically this vector representation, a bunch of 15 numbers, which basically encode the information for sky. And then you can do things like similarity for every word against other words. You can say that these are the most similar words related to sky, beautiful, and you can see that relevant things come up. So in this way, you can build word embedding models and play around with it. Due to the interest of time, let's go to the next steps. So this is more interesting. Again, once you have your feature vectors built, what you can do is things like solve the actual problem, whether it's classification, whether it's a recommender system, whether it's clustering, topic modeling, sentiment analysis, semantic analysis, so on and so forth. And for people who are already solving problems in the industry or people who are looking to make a career out of, let's say, data science, one of the most important challenges in the industry is to frame your problem, because no one is going to tell you go and do a sentiment analysis problem or go and do a text classification problem. They will give you a very vague notion of what needs to be solved. Sometimes they may not even know the right data you have. So that is where you need to apply that mindset as to what could be this task. Is it a classification task? Is it an extraction task? Do I just need to look at entities? Do I need to group things together? So framing your problem is one of the most important challenges in the industry. And after that, you gain your data understanding and the problem understanding in more detail as to whether you have the right data to support this task and so on. And the other part is obviously debugging. So most tutorials you see online or Kaggle and so on, after an X% accuracy, they are done. They don't talk about the other nuances of the industry, like how do you get the buy-in of the executives, or how do you explain your model in an easy to understand format. Like if you go and say that my model has a 0.98 ROC, I'm sure most non-technical folks will not understand, and often they are the key stakeholders in the business. So that is where you need to be able to understand how to explain these things in a simpler format so that they understand it. Maybe talk about your false positive rate, or maybe talk about the number of true positives you are getting, and try to tie it back to business metrics that, okay, this is my hit rate I'm getting, or I'm able to reduce my false positives by X%. So if you talk about those kind of metrics, it is more perceivable and understandable by non-technical people. Because remember, data scientists are the people helping solve the problem. They are not the ones who are driving the initiatives that is coming in from the business side of things. So that gap is something you need to bridge as a data scientist, let's say. And of course, how do you know when your model is ready for deployment? This is always that age-old problem of trying to figure out when do I stop my model tuning or training. So this is where you need to maybe evaluate that, okay, based on the data I'm getting, maybe over this period of time, I'm able to get only X% improvement. If that is acceptable to the business, we go ahead and deploy our model. And that is exactly what the last point tells us, that unless you try out, you will never know how it is performing. So don't just keep tuning your models based on a fixed set of data, like train and test, or whatever, train validation test or cross validation test. Don't say that I'm getting 80% accuracy on test data, because once you deploy your model, you will see it may drop down to an extent for sure. So run some pilots where once you build these NLP models, you deploy it and you actually keep testing performance on real data, because that is when you will know how your model is performing in the real world against new data coming in. Do you need to go back, add new features? Do you need to rethink the architecture? So definitely remember to try things out in the real world. Don't just do train test and stop there when you're working on these industry problems. Let's go into the hands-on tutorials. I think there is some time, so hopefully we can cover both of these. So one of them is the movie recommender system, where the whole context is given. We have a whole database of movies and their descriptions. Can we use some form of NLP to recommend similar movies based on if the user selects a movie? So what we'll do here is we'll do the information retrieval and ranking aspect we talked about, where we look at a movie description, we try to find out similar movie descriptions, and we then recommend those movies. The second problem is more about product ratings. So that is where we will look at e-commerce store reviews, product reviews, and say whether the product was positively received or negatively received, kind of like sentiment analysis. So this is the high-level workflow. Get the movie data set, clean the movie descriptions, build TF-IDF features for every movie description, compare the document similarity for every movie to the other movies. We talked about this using pairwise cosine similarity, and then recommend similar movies based on movie description by finding out the highest similar movies based on the similarity score. So let's dive into this. So movie recommendations with document similarity. Again, I won't go into the types of recommender systems. You can check it out, but this is more of a content-based recommender system because we are focusing only on the content. So let's talk about this. So basically, if I watch a movie, what are the other movies recommended to me? Just like, let's say, Netflix does. Obviously, there are more features and aspects to this, but let's look at a simple recommendation system. So we already have this database of almost close to 4,800 movies. This is called as the TMDB, the movie database. And this is how the data set looks like. A lot of things. The things of our interest are mainly this. We have the title of the movie, which is basically the movie name. And we have the tagline of the movie, which is basically like a one-liner slogan. And we have the overview of the movie, which is like a detailed explanation of some aspects of the plot, some aspects of the characters, and so on. You get it, like the movie overview. So what we have tried to do is we have tried to combine both of these into one single text block or a text document. So you can see here in this code that description column is a derived column where I'm just appending the overview to the tagline. So now our main problem is, based on similar descriptions, can I recommend the movies? So these are the high-level sequences of steps. Again, this is the math behind cosine similarity in case someone is interested to find out how exactly we get the similarity score. Moving into the problem, what we do is we do some basic text pre-processing where we remove all special characters. We keep in the numbers, by the way. Here we are doing lowercasing, removing spaces, fixing up the contractions, maybe if any, and removing the stop words, and that's it. So at the end of the day, we have 4,800 pre-processed movie descriptions. Then we do a TF-IDF feature vector extraction. And as you can see, our feature vectors are each of the words as well as two consecutive words, the bigrams. And you can see here I've used min_df equal to 2. What that means is remove all the words from my feature set or my feature vector which are occurring in only one document, which are occurring only once. What I mean by that is if a word is occurring only once across 4,800 movie descriptions, maybe it is not that useful of a word. So in this way, I can reduce the dimensionality of my problem. And you can see I still have almost 21,000 odd features. So once I have these features, what I do is I compute pairwise document similarity. So what I mean by that is we get each of these 20,000 odd feature vectors for each movie description, and we try to find out how similar movie zero's description is to movie zero's description, how similar movie zero's description is to movie one's description, and you get the point. So we end up with the 4,800 cross 4,800 matrix, and here I'm just showing you the matrix for the first 5 movies. And as you can see here, like movie 0 is around, let's say, 1% similar, 1.8% similar to movie 12. And movie 0 is, as you can see, let's see a bigger one. If I go here, 33. So movie 0 is almost 16% similar to movie 33. So you get the point. So using these numbers, what I can do is I can sort them and try to find out which are the top 5 movie descriptions similar to a specific movie's description. So once I have this pairwise similarity matrix, what I do is this is just some basic processing where I get in the movie lists. And now what happens is, let's take Minions as an input movie. We try to find out that which is the record in our similarity matrix where the movie Minions is occurring. So in our case, that is the first row of our matrix. So what we try to do is we extract out this vector of size 4,800, which means how similar the movie Minions is to all the other movies. And once we do that, we get this similarity vector. And then we can use arcsort on the movie similarities. We use minus because arcsort will sort and give you the top 5 movies, movie indices in this case, using an ascending sorting. Since we want to do it in descending sorting order to get the highest similarity movies, we use a minus here, and you can see it tells us that these are the movies which are most similar to our input movie, which is Minions. And once we extract the names, you can see that the top 2 names are basically from the same franchise, Despicable Me and Despicable Me 2. So now you can build like a generic function on top of this, and you can take some sample movies and you can view the outputs, and you can see that for a lot of them, this makes sense, and movies from the same franchise come up based on the input movie. So using some simple constructs of TF-IDF vectors and cosine similarity pairwise across documents, you can build an effective content recommendation system. And you can even expand this by looking at more complex embeddings like fast text and so on, which sometimes actually give better results. So as you can see for Hunger Games, similar movies from the same franchise are coming up, Terminator, so on and so forth. So now going to the next problem, the product rating prediction system. So the idea here is we have an e-commerce review rating data set where we have a review text which was entered by a customer and they had given a rating. For simplicity, we have made it as a good rating or a bad rating, 1s and 0s. So you can imagine it's a binary classification problem. Now the idea here is to do some basic data pre-processing and try out different types of features, like what happens if I take some count-based features, what happens if I take some sentiment-based features, and finally, what happens when I take some features based on the bag of words model. So once we do this, we can train models on combination of these features and basically evaluate and reiterate and see which is the best model we get based on performance metrics. So here I'll show you kind of a workflow you can follow typically to build a baseline model and try to build on top of that. So this is the last notebook, and then we'll go into the case studies. So predicting some product ratings from reviews. So the idea here is there is already a data set. Again, if it's an open source data set from Kaggle based on some women's e-commerce clothing reviews. I already have the data set in one of my GitHub repositories, so you can use this code or you can download it yourself using the Kaggle API from the command line interface. So this is our, let's forget about all the other categories or attributes for now. This is what it's all about. We have the review. Again, it's just showing partially here. We have the complete text review and we have the corresponding rating, where it's basically 1 if the review rating was more than 3, which means it is a, let's say, a good product, and if it's not, then it's a bad product, let's say. So basically building it as a simple binary classification problem to make things simple to understand. So overall, we have around 23,000 odd reviews. And you can see that it's heavily imbalanced. Like most of the ratings have been positive. Almost 17,500 odd reviews are positive, and only around 5,000 odd reviews are negative. So we do some basic train test split here, and you can see the proportion of reviews again. And then to convert the text data into numbers, we start off with some very simple features. We want to look at the text count-based features, which means the number of times, not number of times, the number of characters in every review, number of words in every review, what is the word density, which is basically number of characters by the number of words, and then number of punctuations occurring, whether there is a title case word in our text, whether we have an uppercase word, completely uppercase word in our text, and so on. So from the text data, this is my feature vector, by the way, which I'm trying to get for every review. Then we go for a classification model. Simplest one is a logistic regression model. So we take in a logistic regression model here, standard fit on the training features, which is this. And then trying to check the performance. So just to motivate, again, I'm sure all of you are aware about this, but for anyone, precision is the positive predictive power of a model. So out of all the predictions made for a specific class, how many of those predictions are actually correct? Recall is the coverage at the hit rate. So out of all the samples of a particular class, how many I'm able to predict correctly? And F1 score is the harmonic mean of precision and recall. So if you see here overall, you can say that, okay, my accuracy or F1 score is 68%. But if you closely look here, this is all 0, which means out of 1 to 71 samples, we are not even able to predict even 1% of these negative reviews in our test data. And if you look at the confusion matrix, that is rightly so. It is like the model is predicting everything as a good product. So it's like a useless model. These features haven't helped the model to be able to separate between good and bad reviews. So now let's think about the domain perspective. So usually, reviews are kind of subjective. Excuse me. Reviews are kind of subjective and opinionated, which means people will express strong opinions, emotions, or feelings about these reviews. So this is definitely a case where sentiment analysis may be useful. So what we are doing is we are using a simple library here called TextBlock. A lot of you might be aware about this. So it uses something called as a lexicon, which is a fancy name for a dictionary. So it will use kind of a dictionary where it knows the parts of speech of a word, it knows the subjectivity of a word, and by subjectivity I mean how much of an emotion or feeling is being expressed by a specific word, and it will also have a polarity score for each and every word, which means the positive level or the negative level of sentiment being expressed by that word. So what it will do is it will go through a full sentence or a document, and it will give you an average polarity score and a subjectivity score. So as you can see here, this is a very positive sentiment text, and you can see the polarity is 0.75 and subjectivity is 0.9 because it's expressing a lot of emotion. Similarly here you can see, again, subjectivity is high because it's expressing some strong emotions, and polarity is minus 0.9, which is like really negative. So the whole perspective here is, can we pass all our reviews through this API, and can we get these two structured features and build our model on top of that also. So that is exactly what we do. We add in these two features called polarity and subjectivity, and we want to now train our model on this and see how it performs. So once we do that, you can see that now we are able to predict close to 27% of the bad reviews. So out of 1271 bad reviews, I'm able to predict 339 of them, which is a pretty good start from earlier when we had only 0. And our prediction performance is also pretty good, where our precision is almost 70% for the bad reviews. And for the good reviews, obviously we have a lot of data, so we are able to predict it pretty decently. So now the thing is, can we still try to do better given that the performance here is still not as good? So that is where we go into now the main aspect which we talked about earlier, about pre-processing your text and then going into the feature vectorization using a standard bag of words pipeline. So that is where we do the same pre-processing as you can see before, very similar, removing spaces, keeping only the alphabets and so on, and removing the stop words. And then this is our pre-processed text. So what we do next is add the bag of words based features. So in this case, we are using just unigrams, but you can experiment with bigrams and trigrams also. And you can see that every word becomes a feature now. And once we do this, we end up with almost 8,500 features. And earlier we had around, let's say, 7 or 9 features. So the dimensionality increases. So now when we train our model, you can see that this gives us a really interesting performance, where this has also jumped up from 89 to 92%. And here from 27% of recall, it has actually become the opposite. Now we are able to predict 70% of the bad reviews, you can see. So definitely a much better model, which we get finally. So now, of course, you can try and tune it more, add in bigrams and so on, and see the trade-off which you are getting for dimensionality to performance improvement. Like if you get only 1% performance improvement, maybe it doesn't really make sense to add in bigrams. So that is the kind of decisions you would need to make as you go forward. But you get the point as to how we started off with some simple features, and we went ahead more, and we tried to see, based on the context of sentiment and so on, how the performance can improve. So feel free to apply similar approaches, where you can even start with a bag of words model and build a baseline model, and then try to improve and enhance upon it by trying out different methods, techniques, even models for that matter, like tree-based models, ensembles, and so on. So that covers our hands-on tutorial. So this gives you some perspective. Again, the code is open source. Feel free to play around with it with your own data, try out other models, maybe get better scores. Now, the last part of my talk is more about the case studies. I'll just cover one major industry case study and some scenarios related to that. So the whole aspect is around this IT service management problem, which I solved a while back. And talking about this, incident management is the problem of interest. So it is one of the key processes in this IT service management domain. You can think about it. And the goal of incident management is very simple. It is like, an incident is basically an issue which is occurring in the enterprise environment, which is being faced by one or more customers or one or more employees. And the idea is, usually this is the flow. They will face a problem. They will come in and either type in by chat or phone, or they will write up an email, or they will even enter a ticket from a ticketing portal. And once the problem is logged, a ticket gets created. Then someone sitting on the operations team will read the full ticket, and then they will try to analyze whether this ticket is of a critical priority or a high or medium or low. And then it will be routed to the right queue, because there are different queues based on the type of problem, if you imagine. And then a support specialist will look at that problem. They will try to go through it, analyze it, and then they will say this is the knowledge article or the sequence of steps which will be used to solve the problem. This is the root cause of the problem, and then they close the ticket finally. So you can already imagine there are quite a number of manual steps here, if you think about it, or bottlenecks. And if you are already thinking like me, you can already imagine that can we automate some of these bottlenecks? And that is exactly some of these use cases, AI use cases, as you might want to call it, or if I want to call it, I would call it a use case for machine learning or a deep learning problem, because again, AI is a more of a marketing term if you think about it. So automated incident priority categorization, by looking at the ticket description or other attributes, can I automatically say what should be the priority of this ticket, whether it should be critical, medium, low. So I want to automatically decide that. The next one is on the routing aspect. Can I automatically say what is the root cause of this ticket so it can go to the right queue, let's say. And the third one goes one step further. It is like if someone is typing in a problem they are facing, can I automatically provide a solution to that problem? Can I build a self-heal system, if you think about it? So these are the three main use cases. The last one is more on a exploratory side, so let's skip that. So predicting the root cause of the priority. So if you think about it, let's understand the motivation for this problem. Like we said, the business aspect of things before we talk about the NLP aspect. So any kind of an enterprise service will typically have their own operations team and their own support agents who will manually classify, tag, and label these root causes, and the priority of these priority of these tickets, if you think. On a day-to-day basis, they will keep doing this. So now the idea is, obviously, since they are doing all these labeling and routing, it leads to a lot of manual effort, wasted efficiency, and a distraction from their true work. So their true work is basically resolving these problems, if you think about it, on a day-to-day basis. So based on the historical incident data per service, can we model on this data to predict the root cause of the priority of the future tickets? So that is what we are trying to do. So now, talking about this perspective, where is the opportunity for machine learning or deep learning models for predicting this root cause, or even predicting the priority for that matter? And the idea here is to look at the historical data. So remember, this is becoming like a classification problem. So we will need to have label data where, let's say, the past 2 years or 5 years worth of data, we want to use that and look at the labels as to what was the root cause, what was the priority of these tickets based on the ticket descriptions, and try to build a model on top of that, so that in the future, if we get some new data, we can potentially predict what would be the root cause or the priority. So this is exactly what I mean, like leverage the historical ticket data, which already has this pre-labeled information where these support specialists took in so much time to try and label this data. And this is where we can parse and process the ticket descriptions and other structured fields like location, product, and so on. We generate these text features then from these description or the unstructured text features. We try to get these structured features in the form of feature vectors, embeddings, and so on. And then we build a classification model, which is like a machine learning or a deep learning model. Again, this is just some sample data, how it looks like with regard to some incidents and like the short description, what is the root cause, and so on. So imagine there is label data like this. So this would be the workflow. And if you think about it, this is the kind of workflow which I had talked about previously when I talked about the NLP workflow. So you can see that this is very similar to that. And this talks about some of the key steps we had done. So one is text normalization, or you can call it the text pre-processing, where I try to look at the text data and we try to remove all these special characters, do some stemming or lemmatization, stop word removal, so on and so forth. And then we come to the vectorization of the feature representation, where we can take in some bag of words or TF-IDF. We can also look at word embeddings, document embeddings. So by the way, this is all about not like combining all the features together, but potential options which you have. So this step is again an optional step. So if you have, let's say, a huge dimensionality feature vector, like we talked about, unigrams, bigrams, maybe even trigrams. So we may need to reduce the dimensionality to prevent overfitting. So that is where we use something like PCA or singular value decomposition and so on. Then we have supervised learning. So you can try out different types of classification models here, like linear models, logistic regression, SVM, and then ensembles, deep learning models, so on and so forth. And the last one is model evaluation, where we obviously have to try out these different models and see what is the best performance we are getting. So that is where we can look at the confusion matrix. And we talked about these other classification metrics in the previous hands-on tutorial, where we look at the precision, the recall, F1 score, balanced accuracy, ROC, things like that. And remember, the last step is very important, by the way. So when you're in the industry, it is not just about the mathematical metrics, but it is also about the what makes sense to the business. So you may need to verify this from the actual domain experts in the field, because they could tell you that once you debug your misclassification step, actually maybe these are some of the features which you should include in your model, aspects like that. So don't just go by only the math based on the internal validation, but also go with the external validation, where you get the domain experts' opinion as to what really makes sense and so on. Okay, so that is all about the workflow we followed. And this is again an example where you can make some sample predictions, and then you have the actual labels, and then you can, so this is like the pilot phase where I'm running and maybe they are also labeling, and then we're trying to see where it's performing worse, where it's performing better, and trying to improve it. And the last part is automating the problem resolution itself. So when the incident is coming in here, instead of going through all these steps, can we automatically use machine learning or deep learning to automate this step, and we provide the resolution here itself? So if you imagine, for past tickets, obviously there was a resolution provided. And now the idea is, can I use some of these reusable components to predict this potential solution based on the past knowledge? Because all my past tickets of the last 2 years worth of data or last 5 years worth of data, they must have been closed with some knowledge article providing a sequence of steps, or maybe a script which could be run to solve the problem. So this is where we use a similar methodology, and we try to map this problem description to a known solution. And if you imagine that there are automated scripts which can solve some of these problems, you can have a self-heal system also. But this part is very important if the model has enough confidence, because you don't want to build a self-heal system where you're taking in every ticket and just saying run script A, B, or whatever C, because the implications can be catastrophic if it runs some wrong scripts, if you think about it. So this is where the human in the loop approach becomes very important, where if your model has enough confidence, you run it. If it doesn't, the human does the right diagnostics, checks it, and provides the feedback to the model whether this was correct or not, and maybe they run the script themselves. So this is something very important if you're looking to build about building about self-healing systems. And the last part is the key behavior of this model. Once the model is deployed, given a new ticket coming in, it would predict the potential knowledge article which could be solved to solve that future incident of the ticket coming in. So there are two types of scenarios here. One is where someone has already filed in an incident, and we basically have a supervised model which is trained on these historical incidents, and we try to give a provided fix, like a label that, okay, this knowledge article can be used to solve your problem, and then it is being solved, let's say, by either the support specialist just directly executing the sequence of steps, or the person themselves goes through the sequence of steps and solves their own problem. And the second one is basically where we provide an intelligent searching mechanism where they can just type in their problem, and we provide them the resolution based on search relevance, if you remember the information retrieval aspect. So just briefly, this is the first scenario where we have the past historical ticket data as well as the knowledge articles which were used to resolve those tickets. And then once a new ticket comes in with the description, we use our model. So finally, we have deployed a deep learning model here, but again, you can try out any type of models. And based on the text classification model, we predicted based on the feature vectors which are going into the model, and we say that this is the knowledge article for resolution, this is the confidence, and let's say if the confidence is above 85 or 90%, it automatically resolves it, or it goes to the support specialists who make the final decision. And the last one is more of a search portal where we have a extract, transform, load mechanism to extract out all the knowledge articles, all the past ticket data, and we dump it into an Elasticsearch index. So in the future, if someone enters a specific search query, we do some pre-processing to it, some boosting and so on, and we search it against our Elasticsearch index, and we say that looks like these were the top 5 similar problems which are very similar to your query, and these were the resolutions provided for them. So you can go ahead and try to solve it yourself, or if you don't like it, you can log a ticket. So why did we go ahead and try to do this also? The reason for doing this is it provides a self-help portal which can lead to reduced number of tickets, reduced SLAs for meeting the ticket resolution, and so on and so forth. So you can imagine it's tied directly back to the business metrics. So always remember the business focus of the problem when you're trying to build a solution, because you can always build fancy solutions, but they need to ultimately provide the right business value. So overall, I guess that is all I had to share. These are my social links. Feel free to connect with me in case you want to have any more context with regard to what I presented, or you have some doubts. I'll be glad to try and help to the best of my ability. And yep, that is all I had to share. Hopefully it was useful. Open for a couple of questions if we still have time.
Yeah, people are actually quite eager to hear answers
Okay.
of their questions. So we have been able to take and enlist a few questions
Sure.
that we got live as we were proceeding. It was, at least to me, it was kind of a short NLP bootcamp, I would say. You kind of
Yeah.
covered many things, and you kind of gave us a very comprehensive GitHub repository of very,
Yeah.
useful resources. And I personally would like to thank you for that.
Sure.
So regarding questions, actually we have got quite a few. So we have time. I mean, there's no bound to time. So would you like to take them one by one?
Sure, go ahead. I think we can take them as long as I'm not eating up time of people's valuable
No
Sunday. But
issues.
go ahead. Go ahead.
I guess we could afford 10 to 15 minutes for the Q&A part.
Go ahead. Go ahead. Yes.
Yeah. Okay. So the first question that we selected is, what are the techniques for aspect-based sentiment analysis?
Okay. So I think there are a few models out there. I would say go to paperswithcode.com and you can search for aspect-based sentiment analysis. And I think there are a few deep learning models out there which are being used for this. The simplest approach would be you build a sentiment analysis model which does the classification. Then you focus on each of these negative or positive sentiments, and you try to do some level of NER combined with dependency parsing, and you try to figure out which are the key entities which are leading to that negative sentiment. There are some other models which are using more of deep learning or attention-based models. You could even check them out. But personally, when I had done this almost 4 years back, 4 or 5 years back, deep learning wasn't that much prominent. So we used a combination of cross tagging, named entity recognition, and dependency parsing to figure out that what are the key entities or aspects leading to the negative or positive sentiment. So that is what I would say, maybe get started with.
So I hope that answered your question, whoever asked it. So another question is, tools for using NLP in SQL.
Tools for using NLP in SQL. Honestly, I haven't done NLP in SQL, but I think BigQuery from Google has added a lot of stuff where you can do machine learning as well as some level of, I'm guessing, NLP in using structured query language SQL. So that is something you may want to check out on. But directly on SQL queries, I don't think I have done like extensive NLP. Yeah.
Yeah, sorry, I was on mute. So the next question is, best metric for document similarity.
Best metric for document similarity. So this is an interesting question again. I mean, there are so many metrics out there. So in general, cosine similarity has performed pretty well for us in almost all use cases, but there are many other types of metrics also. Like a while back, we were checking out KL divergence, but there is something called the Hellinger-Bhattacharya distance. You can even check that out. There is a Mahalanobis distance, a pretty decent one, Euclidean. So Jacquard similarity again. So depends on the type of emphasis you want to provide. If you want to do like a 1:1 matching kind of a thing, like Jacquard is very useful. But I would say start with a cosine similarity or cosine distance, and then you can try out some of these others, and you can see whether it's helping you or not. So build a baseline and try it. There is no like a fixed rule of thumb that this distance is going to be the best distance. Like I said, unless you try it out, you will not know it. So that is the best way to know. But as options, these are some of the common distances.
Yeah. So next question is, what are some good representation methods for documents? And documents here mean longer text.
So yes, good representation methods for documents. You can always start with the basic methods we talked about, traditional count-based methods like bag of words or TF-IDF. You can even try to extract topics using topic models and use the document topic vectors as feature vectors, additional features. You can also use word embeddings or document level embeddings where they try to capture some of the context. But again, remember, basic word embeddings are not completely contextual, because if I talked about this in a recent session on transformers, like if I'm talking about the word bat, it could mean animal, it could mean a cricket bat, a baseball bat, and so on. So all the information together is encoded into one vector. But if you want to consider contextual embeddings, you have to consider the sequence also. That is where you can look at Elmo or the transformer models like BERT and so on, which help you get in that contextual encoding also. You have universal embeddings also out there from Google sentence encoders and so on. So overall, these are the main ones I would say to consider. For really long text, there are some transformer models which have come up recently, I guess, like Longformer and so on. You can explore those. And there are ways to, again, like take in the sequence of words in batches and try to encode some feature vectors. It is essentially some level of hacking, but that is the best way to, again, handle long forms of text. But do check out some of those more complex transformer models if you're really interested. But again, that is pretty advanced. So I would recommend start with the simple approaches first and then dive into the deep learning based methods.
Okay. So when you mentioned about contextual embeddings and stuff, so if my understanding is correct, we do aid the process of contextual embedding learning with positional encoding. Is that correct?
Yes, I mean, for the positional encoding is being done in transformers because everything happens in parallel, right? So it doesn't have like the actual sequence to sequence. So exactly, the positional encoding is being done, so it knows which word is coming before and after which sequence. And the other aspect is also like it does these things like this masked language modeling and so on, where it's trying to guess which word is missing based on the other words. So in that way also it tries to gain some of that context. And since it's handling every sentence or every document separately, and you get these embeddings for each and every word in that sequence finally, that's where I guess the contextual aspect comes in, as a combination of all those things with the self-attention, the multi-headed attention, the positional embeddings, and finally the whole aspect, like when you combine all of these together into the final sequence. But for word to vec, what happens is, since you use a shallow neural network, like all the sentences together, you're finally trying to convert it to this one embedding for every word. So that's where a lot of the averaging may lead to a loss of that context. So,
yeah. So also in transformers, I guess the entire process is one shot. It's not done in an autoregressive way. So for more autoregressive kind of models where one shot learning is not really an option, like the transformers one or the more modern one, what would be the approach you would take to enforce the contextual information along with the traditional embedding?
So it depends. I mean, see, like in transformers, you have different types of models. The autoregressive models, which are there, are basically the generative models, whose core context is about language modeling. So language models are nothing new. Like if I wanted to start with it, I would start with a simple RNN or LSTM or even a bidirectional LSTM, where you can feed in data as a sequence. So the whole concept of language modeling is, I want to predict the next word given these previous words which it has learned. So from that perspective, if you encode the sequence using these RNNs or LSTMs or bidirectionals, it will learn it over time, but it can't learn really long sequences. So that is where if you use a model like this GPT, which uses only the decoder side of things, it handles the autoregressive aspects basically, where it is trying to learn this whole language model with regard to every word which can be generated based on the other words. And then you can fine tune it based on your own capabilities, I guess, whether you want to typically generate the next word or generate a whole block of text using generative modeling ultimately, and so on.
Oh, I see. Okay. I guess that's pretty useful for my works as well.
Sure.
So one last question that we have is, what are some of the EDA techniques one can follow to get more insights from an NLP specific data set?
So EDA, again, it depends. Usually a lot of EDA is not done because we focus more on, like I said, the downstream tasks, if you remember, for machine learning or deep learning. But some examples could be, yes, I can start with finding out what are the top words or top phrases or top entities which are occurring in my corpus by using something like named entity recognition. Then what I can do is, if I am trying to analyze word embeddings, I can see which words are occurring closer to which words in a TSNE or a PCA reduced space. And the other aspect could be that once I do some level of clustering also, maybe I can see which documents are coming close to each other. So that is where you can do some visuals. For topic modeling also, you can do some level of visuals to see, okay, what is the number of documents coming in each and every topic? What is the proportion of it? So again, it depends exactly on the type of task you're trying to solve. And based on that, and based on entities, based on frequencies, or based on occurrences, you can do some level of EDA, but that is the limited nature of it, because after that, it's more about solving the task itself. So I would say it is very task specific, but again, limited in nature, depending on entities, frequencies, and so on.
Yeah. Okay. Okay. I guess that concludes the question answering session and also the session in general. Thank you so much for taking the time out to speak with us. And yeah, we will be looking forward to having more sessions with you, of course. And for the folks that joined today's session, you will find all of the resources that Dipanjan shared today in the link that you are currently seeing on the screen. So yeah, feel free to get connected with Dipanjan. Feel free to connect with us. We are of course here for all of your burning machine learning questions. So yeah, that's it, I guess. And thanks again, Dipanjan, for taking the session with us.
Thanks a lot for having me here, and thanks everyone for spending your time.
Yeah. And thanks to all of our participants. Thank you. Bye.
Yeah. Thanks a lot, everyone. Yeah. Take care.
Bye.